Hello buddies, welcome back to my YouTube channel. I am your Chetana studying in Sri Venkateshwara College of Engineering pursuing Computer Science and Artificial Intelligence Engineering. In this video, let us learn the closure properties of context-free languages, which comes under the subject Theory of Computation. So let us begin with the topic. Coming to the introduction, context-free languages are a class of formal languages generated by context-free grammars. They are recognized by push-down automata, which have a stack to manage additional information. CFLs are important in computer science, particularly in programming language and compilers. They are defined by a set of four variables which comprises VTPS. V stands for the non-terminals, where T stands for the terminals present in the productions, and P stands for the productions that we are generating for the CFL, and S stands for the starting symbol. The properties refer to the ability of a class of languages to remain within that class after certain operations. For context-free languages, these properties determine CFLs interact under specific operations. Understanding these properties helps in analyzing the limitations and capabilities of CFLs. So let us see what are those properties. The main properties which comes under the closure or the union, concatenation, then clean star, then comes the intersection, but it's closed only under the union concatenation and clean property, but it's not closed under the intersection. Let us see how it can be proved. Closure under union. Context-free languages are closed under the union operation. As we know about the union, it's similar to the mathematical union, where we can refer two languages as L1 and L2. Let us see the example. In the example, we have two strings, that is L1 and L2, which comprises the grammar G1 and G2, and which also has the elements as VTPS in both the languages, and if we unite that, we are getting the united part, which is which comes under the language, and it also belongs to the CFL. So we can say that closure under union can be proved by using any of the example, and union can be constructed by creating a new grammar that generates strings from L1 or L2. So this is all about the union. Let us see the next part, that is concatenation. Concatenations is nothing but, as we all know, adding of two strings. Adding of two strings, you can see the example. The dot operator indicates the concatenation of two languages. Context-free languages are closed under concatenation. If L1 and L2 are the context-free languages, then concatenation of L1 dot L2 is also should be a context-free language. Then only we can prove that it's closed under concatenation. To prove that, we can see the example in the right side, where L1 and L2, they have took some of the languages or strings which have different outcomes, and they are finally concatenated it to show that it also belongs to the context-free language. So this is how we can prove that closure under concatenation. Let us move to the next part, closure under clean star. Context-free languages are closed under the clean star operation. If L is a context-free language, then L, the set of all strings formed by concatenating zero or more strings from L, is also a context-free language. Let us see the example. We are taking in the other two operations, we took two languages for proving the theorem, but in this language we are taking only L and it is an arbitrary for CFL. Let G1 be a CFG stating that C of G1 equals L. G1, as you all know, G is the grammar of the context-free language and G1 exists by defining L1 in CFL. So far we have learnt about the closure properties which comes under the union, concatenation and clean star. Now we are referring to the non-closure under intersection. Context-free languages are not closed under intersection. This means that the intersection of two context-free languages may not be context-free. An example is the intersection of the language a power n, b power n, or n should be greater than 0. We can take two languages where L1 is the first language and L2 is the second one, which indicates a power n, b power m, where n and m should be greater than 0. If we take this example, as you can see in the image, the same example where L1 and L2 cannot be intersected. If they also intersect, they can't be under the CFL. So this gives us the information that the closure it's not closed under the intersection. Coming to the complement, context-free languages are also not closed under complementation. The complement of a context-free language may not be context-free. This is significant because it makes certain languages' properties hard to analyze directly. The complement, in the sense, you can take an example of like a language which consists only yes, and the language the complement of the language can be the reversal of the what to say the language, like if a language contains a b strings and a b can be repeated any number of times, you can take the languages a b, a b b, a b b, like that, and in the complement you have reversal of that. So this is how the complement works. And finally, coming to the important implications of these closure and non-closure properties, the closure properties of context-free language impact language design and phrasing techniques. Understanding these properties helps developers choose appropriate language types for specific applications. It also aids in the theoretical understanding of computational limits of various languages classes. Yes, coming to the conclusion part, the study of closure properties reveals key strengths and weakness of context-free languages. While CFLs are powerful in modeling certain structured languages, their limitations in intersection and complementation pose challenges. Future research continues to explore the boundaries of context-free languages in applications of computer science. I hope this video is helpful for all of you. Thank you for watching.